Hey everyone, welcome back to our third lesson in our probability unit. Today we're going to be talking about the idea of and or. So we're going to get away from the simple basic probability and start looking at a little bit more complex probabilities. But before we do this, go ahead and answer question number 1 and number 2 in your warm-ups, and then come back and push play to see how you did. For number 1, it says, what's the probability of a person hitting the shaded region if we know they hit the board? So we know that they're at least going to hit within that rectangle, but now the shaded region is actually the stuff left over from the trapezoid. So what we need to do is figure out the area of the trapezoid, and so you should know that the area of the trapezoid is 1/2 b1 plus b2 times h. I apologize for the very tiny writing there, but it's hard to fit all this stuff into this screen here. And the b1 and b2 are the two sides that are parallel to each other, and the height is the thing that's perpendicular to the bases. So the area of the trapezoid would be 1/2 of 11 plus 5 times 5. And then simplifying this, we end up with 40. So the area of the trapezoid is 40. The area of the rectangle, well, that's just base times height, so that'd be 18 times 10, which is 180. Now, we want the region, the red region. Our event space is the red region. Well, since the trapezoid is 40 and the total area is 180, that means the red region will have an area of 140. So our event space is 140 and our sample space is everything, which is 180. And then that can reduce to 7/9, which can convert to any decimal or percent, whatever you ended up with there, as long as it's equivalent to 7/9. Another way to look at this, though, is the idea of complementary events. So the idea of hitting the red region is the complement of hitting the trapezoid. So remember, the probability of hitting the trapezoid plus the probability of not hitting the trapezoid is equal to 100%, or is equal to 1. So if we were to set up a probability that said, what's the probability of hitting the trapezoid, it would be 40 out of 180, right? Which would reduce to ultimately 2/9. So the probability of hitting the trapezoid is 2/9. Therefore, the probability of not hitting the trapezoid is 100%, or 1 minus 2/9, which would be 7/9, and that's exactly what we got here. So there's two ways to approach this, but keeping in mind that complementary events can help us solve things a lot easier than going through maybe some bigger work overall. And you'll see examples of that probably later on throughout the unit. Number 2, it says a card is drawn from a regular 52 card deck. What is the probability that the card will be a heart with a number on it? Well, first of all, the hearts, there are a total of 13 hearts, because if there's 52 cards in the deck and there's 4 different suits, that means each suit has 13 cards. But within that suit of hearts, not all of them have numbers on them. Like the jack, the queen, and the king don't have numbers. But guess what? The ace doesn't have a number on it as well. A lot of times it accounts for the number 1, but it is not a number in and of itself. It's an A. So if I was going to list out my event space, I would include number 2, 3, 4, 5, 6, 7, 8, 9, 10 of all the hearts. So you can see that that's a total of 9 cards out of, sorry, that's a typo there, 9 cards out of 52. 9 cards out of 52. And then that doesn't reduce, so we'll just leave it like that. If you converted it to a decimal or percentage, as long as it's equivalent to 9 out of 52, you're okay. Now with that said, let's go ahead and get into our unit, or our lesson for today. The objective says I can determine the probability of an event that has requirements. So what does that mean? A requirement means that we are looking at not just a single event, we're looking at a composition or a combination of events. Okay? But before we get into that, let's talk about the word and. Let's talk about the word and. You see, in mathematics, oftentimes we think of the word and as addition. But when you're talking about probabilities, you're actually not adding, you are removing, you are making a set smaller. And here's an example of what I mean. When you're talking about a subset or an and, you're talking about a subset of two sets that two sets have in common. So if we look at that set notation, like if we have the sample space or the event space, remember we write the squigglies and we list all the possibilities? Well, here's an example of a subset. Actually, before we get into that, the word and can be replaced with the word intersection when we're talking about subsets, and set notation is what it's called. And we use the symbol of like an N. It's just like an upside down U, okay? It's not an N, but it's an upside down U, I guess you can think of about that. These are synonymous. When I hear the word and in probabilities or set notation, I'm thinking of the word intersection and I'm thinking of the symbol N. And I think this is a way that students see this sometimes is, oh, to finish this off, I can just draw a line across here and I get an A for and. Okay, just to help you see that, draw a line across and I get an A for and. Okay, so that means and. If you see the symbol, it's and. If you see this word, it means and. If you see and, it means intersection. Okay, you're going to want to put that in your memory bank somewhere. But let's take a look at an example of a set. So here are two sets. We have the set of -2, 1, 2, 3, 5, and 8. And we have the set of 0, 2, 5, 8, 9, and 11. And I am asking for the intersection of them. Or another way of saying that is I am asking for where both sets have the same number. So the way I would word this is this. I would ask this question. Is -2 in the first set and the second set? No, -2 is not in the first set and the second set. You see, when we see the word and, we think, oh, we're going to add everything together, so we're just going to put all of these with all of these. No, that's not the case. When we are saying and, we are saying that that number or that event must be in both things. So this number must be in both sets, and then in probability, this event must be in both of the events that we're talking about. And you'll see an example of that later. But the question here, when you see the symbol, the intersection, we are saying which numbers out of these sets are in both of the sets. And so we would underline the ones that are in both. We can see that 2 is in both of them. We can see that 5 is in both of them. And we can see that 8 is in both of them. And so the intersection of these two sets is 2, 5, and 8. And again, think of the word intersection. We are looking for the places where those two sets cross each other or where they have the same things in common. Okay? So they cross each other at the numbers 2, 5, and 8. If you think about the intersection of two streets, the intersection is all the points that they have in common. So it's that big square in the middle of the two streets, right? In between the street lights, as it were. Okay? Those are that is the region that both the streets have in common. So it's the intersection, or it's where both this street and this street exist together. Okay, so now here's the other part. The word or. The word or is the subset that either set contains. So the word or is actually going to give me more options, okay? So the symbol that I use for that is actually the U, and we say that that is the union, So here we drew a little line here to represent A. Intersection is A and. For the union, if we draw a little line on top, I know it's kind of funky, but you can see that you get an O. So or. Union is or. Okay? So if you hear the word or, you're thinking union. If you hear the word and, you're thinking intersection. And so let's go ahead and take a look at the same two sets of numbers, but change the symbol in between. So now we are looking for the union of these two sets. Well, what's union mean? Union means a number that is in either set. Okay? So here's the question. Is negative 2 in either this set or this set? Yes, it is. So it's part of the union. Is negative 1 in this set or this set? No, it's not. It's not in either of them. So negative 1 doesn't count. And so basically what we're doing when we're talking about a union or an or statement is we're listing all of the numbers in either set all in one set. Notice we didn't repeat numbers, so we did see that both of them have 2. We don't write 2 twice, we just write it once. Where you are asking the question, is this number, whatever number you ask, in either the first set or the second set? And so I know this can get really confusing when we hear the words or and. We actually sometimes think the opposite of what it means in terms of set notation or in terms of probability. Notice and makes the set smaller, right? Here we had a set of 6 different things, and here we have a set of 6 different things. But when I found the intersection, it was a set of only 3 things. Where union or makes the set bigger. So we had a set of 6 things and a set of 6 things. It actually turned into a set of 9 things. Okay, so here's what I want to, maybe this helps. If I were to ask you this question, do you have a sandwich or a taco in your lunchbox? I don't know, I'm just making things up, right? Do you have a sandwich or a taco in your lunchbox? Well, notice that is expanding the options. That is giving the person more options to pick from, not less. Whereas if I said, do you have a sandwich and a taco in your lunchbox? Well, that limits the possibility, right? You are less likely to have a sandwich and a taco. You would have to have both of them for you to have a sandwich and a taco. So that's my point. You are getting less of a possibility when you talk about and. But you are getting more of a possibility when you talk about or. Because what is the possibility, or what is the probability that the person, when you ask the question, do you have a sandwich and a taco in your lunchbox? You would have less of a chance for them to say yes. But if you went to them and said, do you have a sandwich or a taco in your lunchbox, the chances of them saying yes is improved because you're giving them more options to choose from. So anyways, go ahead and take a minute to practice these 2 things. You have 2 different sets, and I'm asking for the union and the intersection. So go ahead and hit pause, and then answer it, and then come back and see how you did. For the first one, we are looking for the union of 9, 11, 13, 15, 17, and 10, 11, 12, 13, and 14. So here I'm looking for the union, I'm looking for the or, so I'm going to list anything that is in this first set or in this second set. So you're going to get anything that's listed basically, you're just not going to repeat it. So we got 9, 10, 11, 12, 13, 14, 15, and 17, or. For the second one, it's asking for the intersection. It's asking for the and. So we're looking for the numbers that are in the first set and the second set. And so we can see that the number 11, 13 are the only 2 numbers that are in both the sets. It's in the first set and the second set. All right, with that said, let's go ahead and take a look at this a little bit more complicated, right? We've got 2 6-sided dice, so we're looking at 2 die, we're rolling them like in Monopoly, right? And this is why some people are so good at Monopoly, because they know the board spaces that people are more likely to land on based on the probabilities that you will roll certain numbers, okay? So 2-sided die are rolled, 2 of them, list all the possible outcomes. Well, if I list all the possible outcomes, I could get a 1 and a 1. I could get a 1 and a 2. I could get a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6. I could get a 2 and then a 1. That's different than a 1 and then a 2, right? Because one die, let's say I had a red die and a green die to make sure I knew which one was which. if I roll the die, the green one could be 2 and the red one could be 1, or the green one could be 1 and the red one could be 2, so it could be flipped. But anyways, these are all the different combinations that I can get out of rolling 2 die. Notice there are 36 possible outcomes. Why is that? Well, that's because you have 6 options for the first die. You have 1, 2, 3, 4, 5, 6. And then you have 6 options for the second die. 1, 2, 3, 4, 5, and 6. So you have 6 times 6 different outcomes because you're rolling 2 die. So we would say 6 squared. If you were to roll 3 die, how many possible outcomes would you have? Well, you would have 6 times 6 times 6, or 6 cubed. Anyways, that's all the possible outcomes. Let's go ahead and take a look at some examples of what and or probability looks like. Well, B says, what is the probability the first die is greater than 3? Well, this is just single event. What is the probability that the first die is greater than 3? So the first die greater than 3 would mean that it's either a 4, a 5, or a 6. And so you can see that we have 18 out of 36 possibilities. The probability that the first die is greater than 3. So that reduces to 1/2 or 50% or 0.5. For question number C, or part C, it says, what is the probability that the second die is greater than the first die? What's that mean, greater than the first die? Well, that would mean all of these cases, that the second die is greater than the first die. So if the first die is a 1, that means the second die has to be a 2 or higher. If the first die is a 2, that means the second die has to be a 3 or higher. If the first die was a 3, then the second die would have to be 4 or higher, and so on. So what's the probability that the second die is greater than the first die? Well, we count up all those possibilities. We can see there's 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 out of 36. And then that can reduce to 5 out of 12. But now let's get into the idea of intersection and union, or and or. Now, what is the probability that the first die is greater than 3 and the second die is greater than the first die? Okay, so we are trying to combine question B and question C with the word and. So what is the probability that this happens and this happens? Well, if I highlight all the different possibilities again, okay, so the check marks here, the red check marks are the ones where the first die is greater than 3, and the purple check marks are all the places where the second die is greater than the first. You can see that there's somewhat of an overlap here, that these 3 cases are when both of them are together, or both of those events occurring. Now I'm using the word and. So think about it this way. Is this case a case where the first die is greater than 3 and the second die is greater than the first die? Well, the answer is no. Not both of those cases are true. It's only the second case that's true. If I go over here, is the first die greater than 3? Yes. Is the second die greater than the first die? No. So not both of those cases are met. Well, where is both of those cases met? Here out of these 3 things. So our probability here is 3 out of 36, which reduces to 1/12. Okay? So notice my notation. The probability of the first is greater than 3 and second is greater than the first. Notice when I use the word and, when I use the word intersection, I am reducing my possibilities, not increasing them. I'm lowering them. For parts, so we'll call that event 1 and event 2. So we could rewrite question D to say the probability of event 1 intersect 2. For question E, it says what is the probability that the first die is greater than 3 or the second die is greater than the first. So if you think back to what I just said, or increases your probability, it adds to the list of things, as it were. Is, in this case, 1 and 6, is the first die greater than 3? No. Is the second die greater than the first? Yes. So is this saying that the first event is true or the second event is true? Yeah, it is. It's meeting one of those requirements. So this one counts. In fact, anything that's checked off is going to count. And so as a result of that, or you just go through, if you need to, you go through each individual one and check off all the different options that could hold to either this or this. And so we can see if I check off all those options there, all of those red check marks work in either one or the other. All of those other check marks that I just checked off work in either one or the other. So how many of those cases meet the requirement of event 1 or event 2? Well, that'd be 30 out of 36, which is 5 out of 6. Let's go ahead and take a look at a last example here. I like tables because it helps us understand things in a little bit more concrete way. There are two different exam options for AP Calculus, A, B, and BC. Those are two AP tests that a student could take. Both exams and how many students received each score are listed in the table below. So these are actually global scores from a few years ago. Actual results, numbers of who got what. A score of 3 or higher is considered passing. So you can see that a lot more students take the AB exam because AB comes before BC. And then you can see that the 3s, the 4s, and the 5s are considered passing. Okay, 1s and 2s are not passing. And then obviously the 5 is like the highest you can get. So the first thing I'm going to do is I'm going to figure out the totals. So the total of students that took the AB exam, I'm going to just add up that whole column, or that whole row there, is 317,000. For the BC exam, I'm going to add up all that, and I end up with 133,000, just so we have our bearings. The total amount of people that took the calculus exam of either type would be those two things added up, which is 450,000 students. In question 1, it says, what's the probability of BC? What's that mean? It means what's the probability that the student took the BC exam? Well, how many students took the BC exam? What's our event space? Our event space is all of these added up, which is 133,000. And then our sample space is going to be the total amount of students that took a calculus exam, so 450,000. We can knock off a bunch of those zeros, and then we can divide if we want. We end up with 29.556%. Number 2 is an intersection, and that's the purpose of this lesson, so make sure we're clear on this. What is the probability that a student took the AB exam and passed? So if we were to identify the students that took the AB exam, well, let me take a step back here. The students that took the AB exam are these guys, these guys, these guys, and these guys, and these guys. So these are all the ones that took the AB exam, but we also wanted them to pass. So they must have passed as well. So we're going to get rid of option 1 and option 2 here. So these are the 3 sets where the student took the AB exam and passed. So notice it reduced the amount of students. It didn't increase the amount of students because we removed the AB students that didn't pass. So we would add those 3 sets up. That would be 182,909. And then we would say out of 450,000 people. So 40.64% took the AB exam and passed. All right, well, question 3 says, what's the probability of event 1 or event 2? Or, sorry, let me rephrase that. What's the probability of getting a 1 or a 2? Well, or means it could be either this or this. So which ones are ors? Well, which ones are the ones? The ones are this guy and this guy. And which ones are the 2s? Well, that'd be this guy and this guy. So what we're going to do for the ors is we're going to include anything that's a 1 or anything that's a 2. So we're going to add up all 4 of those sets. That's 159,893 over 450,000, which is 35.5%. So in other words, 35% of people in the world, students in the world, fail the AP Calculus exam. All right, for number 4, it says, what's the probability of a BC student, of a student being in BC or getting a 5? So again, is this group of students BC or a 5? No. Is this student BC or a 5? No. This student, no. This student, no. Is this student BC or a 5? Yes, they're a 5. So they meet the requirement of BC or a 5. They wouldn't meet the requirement of BC and a 5, but they do meet the requirement for BC or a 5. Okay, then we have this group. That is BC. It's not 5, but it is BC, so it's BC or a 5. So this one counts, this one will count, this one will count, this one will count. Will this one count? Is this BC or a 5? Well, yes, it is. It is BC or a 5 because it is BC. It is also a 5. So is it BC or a 5? Yes. So we're going to include all of those red ones that are marked there as our event space, which is 191,962, over our total, which is 450,000, which is 42.658%. All right, that wraps up our notes. When it comes to intersection and union, we're going to talk more about that later in some other notes, but hopefully that gave you an idea of the concept and the words of and or and the symbols, the N and the U. But go ahead and finish out your assignment here by answering the questions below, and I will talk to you later.